Good afternoon, everyone. Welcome to the people that are here in person and to the people who are connected from the web. It's a pleasure to be here. And today we have the first talk of this research unit in artificial life. So we started with an important speaker, because Professor Takeshi Ikegami is a leader in this field. And as often the case, he started as a PhD in theoretical physics. He started, he was telling that he was working on spin glasses when he was, at graduate school and also later. So he has this background, and then he was hooked by this artificial light that you see from his T-shirt. That is, speaking on his own. And of course, he's a very good friend of the CRT. He has many friends here, and really we really appreciate that you visit us. And without further ado, please, Takeshi, is your first.
So, Aditya, thank you so much for inviting this seminar. I'm really happy to be here. And the last time I came here was maybe more than 15 years ago, right? Where I studied oil droplet moving by itself, which I started with Martin Hendrick. Now he's in Trent University. So first of all, I should express my deepest sympathies to former Prime Minister Shinzo Abe, because he got killed by a deadly bullet today, and he passed away after 1-2 hours. So I don't know whether he is a good politician, but he loved by many people, right? Like Johnson in UK. So I'm very shocked, and then there's a sort of depressed mood in Japan right now. I just got the mail from many of my friends that got shocked, but now it's so this I tried to do my best to deliver the sense of artificial life and what I'm doing now. So I already yes. So I wasn't quite sure this seminar was to the general audience or the physicists or not. So I tried to make it in between. So anyways, one of my interests is the collective intelligence. What happens? There are many, biological systems or agents get together, and what sort of a new intelligence is emerging on top of it. Right? That's my interest. And especially, I said it's called Genki. Genki means sort of vitality in Japanese. So when you do cell experiment, some of the cell is very vital. Very, even though from the same genetic system, but some of the cells are very, very active, and some of the cells are not so active. But what makes difference is because we pick up from the same soup, put in a different well, but the behavior won't be different. So same DNA doesn't tell us that we can expect the same behavior, right? So in the conventional biology, that people say, okay, if you understand DNA, you can understand everything. But that's not true. We really have to understand how each agent is interacting with others. That determines, the real biological phenomena on top of DNA sequences. So you can also say that this is what called genotype, which is coded by the gene. This phenotype is like this. This is the phenotype. So even if you specify what the genotype is, but still the phenotype can be many. So that there's a bunch of flexibility or one-to-many mappings from genotype to phenotype. That's what we understand these days, what we see in the biological systems. So now, I give you a little introduction to artificial life. Right? So it's back in 1987 in the United States, Los Alamos, that Chris Lanton started up this artificial life. And that was a very interesting conference, which was combined of scientists from physics and computer science and a little bit of biological people. So it's a nice interplay between computer physics and biology. So this is one of the typical artificial life model. So you need only 3 rules: separation, alignment, and gathering. Only 3 rules that you can make a swarming behavior. Like this one is making a cycling behavior, but you don't need any other thing. Only 3 rules necessary to make a rule. So that's what this kind of simple thing is that everybody was so attracted. Swarming behavior is complicated, but they only need 3 rules. But then I thought, so this one is something that I did with sort of differential equation that physicists tend to make a model. So the first one is separation, second one is alignment, and the third one is the sort of cohesion, together thing. Right? So these 3 rules, then we can make equations for swarming behavior. Right. Then I noticed that like 30 years ago, we have only a small size computer, so we cannot simulate like millions of words, millions of agents. But now we have GPU machines and supercomputers, so that we can increase the number of agents, right? So that's what I tried. So this is the periodic boundary condition. So you go this way, the other one is coming back from the other side. If you go up, coming back from down. If you go to the front, then you come back from the front to back. Right? It's a 3-dimensional periodic boundary condition. Now this one is the 2048. Then I increased to almost 16,000. It's something that a different structure emerges. Then to the 130,000 elements, then the images become so different, right? So you have more big bubbles with some strange, pipes coming up. Then again, this is 554,000 stars. So the initial, image of swarming is very different once you increase the number of agents. That's what I understood. And so, for example, like if you take the order parameters, which is the Lipschitz order parameters, so simply the order parameter is to characterize the swarming behavior. Either the swarming, and then the vertical line is simply the kinetic energy. So how fast they can move around, and then the horizontal line is order parameters that characterize how the agent is aligned their head. The heading direction is more aligned, then it goes to 1, and it's more random, they go to 0. The more first, they go to up to the 1, and if it's more random, but it's slowly moving, then it goes to 0, right? So we typically have a different basically you have 2 big streams, attractors. Excuse me? No, this is deterministic, yeah. So for this deterministic system, one of the interesting points that I found was that increasing the size of swarm. So there's a bunch of swarms coexisting at the same time, right? Some of the size is less than 1,000, right? Then the black line is so-called fluctuation, right? The 2-point fluctuation we calculated, but then the fluctuation goes up and goes down, but then the next fluctuation emerges, which is red, described with red curve, which is a density fluctuation. First of all, the heading direction is fluctuating. Then it's switched to a density fluctuation. So 2 different fluctuation emerges in the swarm. Depending on the size of the swarm, inside the fluctuation is different. That's one of the messages. The interesting point is why this is important. Because when you participate in the swarm from the outside, then the response strength is proportional to the fluctuation. That's what fluctuation theorem tells us, right? So measure the fluctuation, then you can understand how it can respond to the perturbation from the outside. So here that you can see that this swarming behavior has two different response to the external stimuli. One is when you change the density or when you change the direction of the swarming. So that's one of the things that I did. So the big swarming behavior, even if you little bit just increase the number of agents, then the swarming behavior will be very different. So the size of the agent is a big parameter to understand the collective behavior. But then there's a bunch of different types of studies I studied because I thought it was interesting. Then I switched to more biological phenomena. Right. So this one is the honeybee. Right. So I put so this one is a collaboration work with people from Illinois, urban Champaign. This is Gene Robinson, who is famous for honeybee hive, honeybee studies. Then they put a QR code on each back of the insect, right, at the bee, so that then they can make a two-dimensional honeybee hive like this, right? So honeybee hive is always have to be perpendicular. Then you put the video camera here, right? So that you can take behavior with the video camera. Right? But because you have a QR code, you can detect which individual goes which directions all the time. And then we did like 7 days, 1 week, continuous recording of the behavior. Right? So it's a very interesting stuff that came out from this study. I don't go into the detail this time, but sometimes if you see this is the index of each individual honey bee, and then this is time. And then when you see the black point is the way that the kinetic energy goes up, means that they become so active. Right? So some of them are active, some of them are not. Then a certain period of time, there's a synchronous bursting behavior. So synchronous activity is coming out. Right? So that's what I thought was interesting. So I looked into what's the bursting behavior of the honeybees. Right. So it's that's one of the things. Then I found that when you open up the door, then you can find some the interesting things that happen. So the door, even if it's artificial, but you can open the door. Right? So here's the door that you can open. So the bees can go out and then coming back later. Right? So even if this is the artificial honeybee hive, but it's connected to the external environment. So they go out, they come back. They go out, they come back. Then when you open the door, you see, so we open the door after 2 days and a half. Then what I mean by foraging is the bees went out. Then after like 3 days or 2 days, dancer emerges. So when they come back, the dancing behavior emerges. Right? So when dancing behavior emerges, then there's an interesting birthing behavior. Right? So this is the green thing is the birthing behavior. The violet curve is the bursting behavior of the activity. So it looks like, once you open the door, then the bees has a synchronous bursting behavior. And it seems like this bursting behavior triggers the bees to go out and then get the information to come back. So it looks like the honeybee hive itself can have a spontaneous burst. That's also interesting. That without opening the door is closed, but bees are still, shows a big synchronous burst. But when you open the door, right, then this bursting behavior is corresponding to something outside of the environment. So I think this bursting behavior is a response of the honeybee hive to the environment. So there's some interesting things happening. Yes. Synchrony in the activities. So it's not the direction, but how many bees are active in a way that it's moving around quickly, and then everybody's moving quickly. Yeah. So I'm gonna skip it. So then I got interested in skip this one, but there are many interesting things happen in a group, biological colonies. For example, this is ants, so that we can record all the ants' behavior and see what kind of behavior that emerges from this. And also, I looked into this. This is the web services, which is posting a photo of your moon with some tags, and then how the tag is coexistent with the other tags, and you can find some speciation of the tags in the website. So that's another thing. So I'm sort of interested in how it changes over time. This tagging behavior of the community is forming over the time. But this is very artificial systems. So small the summary of what we're going to discuss and what we have found so far is that many of the collective behavior is excitable media, like neural systems. We think that the neurons are zeros and one, or excitable or quiet state. But it's also true for the honeybees. It's also true for the ants. It's also true for the web systems. It's also true for the many other collective systems that they are excitable media. And excitable media is a common property of those collectives. And the second is that so we can use temperature to characterize the grouping behavior. Because we calculate the kinetic energy, means that the activity of the individuals. And then maybe the temperature is something that we can understand from these collective behaviors. But temperature is something like it's borrowed from physics, but maybe you can introduce into this biological phenomenon. And then susceptibility of the collective is something like a fluctuation increasing is the way that the collective is responding to the fluctuation, stimulus from the outside. Then some network structures. So I try to hurry up it because I want to talk about this tetrahymen. That's the main topic that I'm going to discuss today, which is little ciliate tetrahymen. It's a small little insect which exists in the water. And the difference between protozoa and this one never dies. They can infinitely replicate and can exist forever. But the protozoa can only divide like 100 times or 150 times. So we use this one to understand what's the collective behavior of this hymen, tetrahymen. And then usually the people think that tetrahymen doesn't make a swarm because it's a very small brain. It's not brain, but a chemical network inside. And people don't think that they are that intelligent like us. But we will see whether this one shows some interesting behavior now. This is what you can see. So we can trap all these small agents and then measure these activities and how they interact with each other. By the way, so this study is pretty much ongoing, so that there is a bunch of questions that I still don't understand. It's something that I want to share this findings that I want to discuss with you. So the way that we do is that tetrahymena so this is something the setup that I'm using, which is 800 micrometers, which heat plate on top of it. So we put the heat plate and then keeping up at the 35 degrees, which is a little bit high, and put the glass plate on it. Then there's a what I call some food, what we call culture. Culture is here. So hot plate, culture, and then glass plate, then put the water, then there's a tetrahymena inside. So the tetrahymena is moving around. Then this time we put the microscope on top of it, so that we can record through the microscope what this tetrahymena is moving around in the space. So this is what does it look like. So you can see a tetrahymena. This thing you can turn the light. Yeah. So you see those little creatures moving around. Then, so using some of the algorithm that we can see, how so different color indicates different individuals. And this one is no dividing. This one is going to divide. So once they are interacting with each other, then the blue one is slowing down a little bit. Then they're going to divide. So you can identify all the events through time, and then you can track every individual, how they, when they divide, and how they behave after they divide, after they have to divide. And then for the fixed number of this agents that you can see how they are moving around, around each other. This one is I don't know, but this is a natural phenomenon, right? Yeah, so I believe that this is something that which is may not be a deterministic, right? But I come to the point. So so the question is, of course, what is the vitality, right? As I said, one of the well shows quite active, but one of the other cells is quite inactive. So what determines it, right? So as you can see, this one is not so active, but this one is up. All these the tetrahymine has the same genotype and the same numbers of the agents put in the same well, different well, but it's coming from the same genotype set. But you see, these are the different. I mean, I think it's a different. This one is more active, this one is not. But that's coming back to this point that genotype to phenotype is not one to one, but one to many. So so this is something that this is the distribution of kinetic energy again. So the activity of this each agent. I didn't explain that. Yeah, but kinetic energy is like usually like this form. So this is the velocity, and velocity to the square divided by 2. That's the kinetic energy of each agent. So I'm measuring. So when this is moving around, so you can measure the velocity so that you can calculate a kinetic energy. This one, right? So then I calculated for this one. It's only one single agent, and then I calculate this energy, kinetic energy, and then how it distributed. So do you see here? It's always like almost straight line, but the vertical axis is in a logarithm scale, and then horizontal scale is just a normal measure. So yeah. It's a logarithmic p equal to something like this. So minus line, so the p equal to exponential x is something that we say exponential distribution. So when there's only one individual, it's almost like exponential curve. And when there's so this is the first 10 minutes, and then it's the last 10 minutes. You see, some of them are a little bit concave in the lower direction, but still it has a nice exponential curve. And when you increase the number of agents, like this is 4 individuals, this is 8 individuals. So for 4 individual cases, they seem to have some, still they have a single line, but a little bit concave. This one is also a little bit concave, but I overlaid all these lines so that you can see the diversity of the lines. And I don't know whether you can see this is exponential curve or not, but that's what I found here. And from the paper, there's some review papers by with the group that says once you have that Brownian motion, and then the distribution becomes exponential. So this is just a simple mathematics, but what we call Fokker-Planck equation, or the Langevin equation, shows that the Brownian motion with some little friction, then it shows exponential distribution of the kinetic energy. So one of the conclusions is that, okay, so this Stroheiminer shows the Brownian motion was something else. Then we compared the distribution of kinetic energy with others. Right? Means that this is what we call the Janssen-Shannon divergence. But this is simply if one has kinetic energy of this form, right? And the other one has the kinetic energy of this form. So these are the differences. Right? So these differences is computed by the formula. In more sort of technical speaking, this is A and this is B. So basically what we have to do is divide a distribution curve divided by the other one and take a logarithm of that. So that's what the Kalbach-Leibler divergence is coming from. And then, but in order to symmetrize this one, is like this way. You just divide by PA plus PB and XBC. Then you just compare PA plus PC plus EB divided by PC, and gives you Janssen-Shannon divergence. But it's just a technique. What we are doing is how distribution curve is similar to each other is measured by the JST. So what we found here is that so the horizontal line, how many numbers of cells that exist in the cell. And when you increase, and then the light blue color is something that we found in the initial case when we put agent cell. And then more concrete, more blue is corresponding to where what time passes. So when you see this one, spot 1 is very early stage, and spot 2 is after 1 hour. After 1 hour, and then the second, when there's a 2 cells, 3 cells, 4 cells, 5 cells, 6 cells, 7 cells, or 8 cells, always, the similarity is less and less. Means that when the JST goes up, means the lower one is 0, means that everything is completely the same. So when the JST equals to 0, this one is exactly the same distribution. When JST equals to 1, it's totally different. Right? So it looks like always, from the light blue to blue, that histogram goes up. Means that first of all, it's more similar, but then gradually it is diversified. Right? The curve is. And what does it tell us? That's something I still don't understand. So I tried to look into this some of the curve, which is this is the JST value for the well. So each well, so this is the blue one on the left most left side is random particles. So comparing with the random particle, the tetrahymena with each other is much similar compared with the random particle interacting with each other. When I say random particle, it's just not a random particle, but the independent tetrahymena plus another independent tetrahymena. And they are not interacting with each other, but we can measure this JST. Right? So that's what this blue point in the leftmost zone plot of the leftmost edge. But then if you increase the number of cells, and as you see that the JST is going down, means that when JST equals 0, it's very similar. It's this is means equal, and this is totally different. Right? So because it's comparing with the random one, that JST is much lower, so that the agent is not randomly creating those GST, but they are most likely that this is the same thing for the well. But this one is for computing the same thing for each individual. So for each individual, their GST goes up, means they become different. So it's a bit complicated, but each cell, yeah. The pre and post is that because the people say that once you pick up the tetrahymena and put in the well, and you have to wait for a while, because they say that they have to accustom to the environment. So after 30 minutes, it's a first spot. And then wait 30 minutes. And again, there's another spot is coming. 30 minutes. And then, yeah, this is pre and post is 10 minutes of each one. And this is 10 minutes for 10 minutes here. So we are taking this one, this one is called spot 2 of the pre and post. So I think they almost, relax to the QSI stationary state. Then we pick up each individual, and what's the kinetic energy curve look like? And looks like for the individual thing, it goes up, but as a well, that goes down. Or very similar. For each well, it seems very similar, but each individual it becomes very different. I come back to the point there. So in the case of replicating tetrahymena, is like this. So first of all, we have tetrahymena. This is the temporal behavior of only in x coordinate. This is the two-dimensional thing, so we can just measure x coordinate how it changes. The first one is this. It's divided into two cells. Right? So we have two lines, and then divided into two. Each of them is divided into two cells. So we now have 4 cells. Then each of them divided into 2, so that we have 8 cells. Each one has its own behavior. So the question is, I think it's one of the interesting questions is how the distribution changes over time, right? So I think interestingly, that's the first one, kinetic energy distribution, and it's the second generation, third generation, fourth generation. Their behavior looks like similar, right? And then this is another example. The first one is that, and the second one, third one, fourth generation. Their behavior is also same. It's quite similar. It's very different from the previous one, right? That one, but it's pretty similar to the first. So it seems like even if there's the same DNA, but it's a different behavior. But if you're divided from the one individuals, they always seem to have something. Maybe it's a style of motion or dynamics. It's inherited to the offspring. So that's why those agents have the same distribution curve. Again, this is another example. It seems like this one is a bit elevated in the third generation, but still it's different from others, right? So that it's apparently there's a inheritance of something to the offspring, even though there's no DNA changes. So it's some other things like a somatic chemical component of the dynamics itself can be inherited to the offspring, right? This one is. So one of the most interesting questions I think is what's the difference between the population created, spontaneously at the same time. So picking up 8 tetrahymena from the group and then make a group of 8 individuals. And then the other one is making things from the beginning, right? So what I'm doing is, so this is gene pool. There are many tetrahymena. So picking up 8 individuals and make a group. That's one thing. And picking up 1 tetrahymena. Then he's going to divide it into 8. what's the difference between tetrahymena generated from a single agent and tetrahymena with the same gene, but it's not from the same individual, but it's randomly picked up. So that the behavior looks like this. This one is generated from the same agent. One is from yeah. This one is from the single cell, and this one is from the immediately from the something different, right? I mean, I see the difference between this H ubiquitous cell and the H cells from the same clonal population, but it's not the same character. Same mother. So I want to understand what makes the difference. This one is why it's different. Yeah. I don't think so. Yeah, I'll come back to the point here later. So one of the individual analysis that behavior is always like this. So tetrahymena goes straight and makes turn and goes back to turn. So there's a frontier work by Libra, his Libra group, Libra in Princeton. They studied the tetrahymena also. I didn't notice that when I started this work, but Libra did single cell not interacting with each other, but looking at the single cell and how the single cell behavior does look like. And he tried to understand that each single cell is characterized by the turning point and also straight line, right? So computing a velocity of this part and computing angular momentum of this. So straight velocity and then angular momentum is the two variables that is he thinks is important for characterizing the state space of this behavior. Then I calculate again this divergence, which is the difference between the two behavior. And then we try to embed it into 2D space to see what the difference is. So one of them is extracting samples of a single individual. So they are not coupling together. It's more like a individual behavior. And then this one is the 80 individual from the same corner. And then we embed it into this 2D space. So the orange point and the blue point it's a little bit overlapping, but it's different, right? So once you have 8 individuals from the same group, and then so this one is a single. Maybe easier to write. So on the left you have you prepare the single agent in a single cell each well. So we have 8 wells like this. So you can compare the distribution function for each cell, each well. And then you can also compute the 8 individual cells that you're moving around. And you have 8 curves. And then comparing with this and this, what happens? Is there any similarity between this and this? And it seems like this one is not just a linear combination of the single cells behavior. It may be something different. And also this one is again comparing with the one that is coming from the single cell, dividing into 2, and then dividing into 4, and dividing into 8. Now we compute the kinetic energy of this one. So this one is coming from the same parent, same mother. This one is totally independent from each other. And this one is interacting with each other, but it's not the common ancestor, right? So this is common ancestor. This is individual, independent. And this one is just a random coupling of 8 individuals. So when you see this, this the big blue one is from a single cell, and then from a different parent. So it's always, covering the entire space. But the orange one is from this unrelated, means that from this. So even if there's eight agents in single well, but randomly coupled agents, and then also the agent coming from the same parent has a different behavior. It's more diversified in this diagram. And it's interesting when you see the agent. Sometimes they are totally synchronized. Their behavior is not so much, within together. Yeah, looks like sometimes. However, as I said, their behavior is quite similar to each other, right? So again, that we looked at this power, it's a median average of this same from the well. So this is a median of kind of genetic distribution of each cell. It's a Barbara means that the cell is randomly pick up 8 randomly well, or it's coming from the common ancestor. And the common ancestor well is always diversified compared with the one that is created from the soup. And so this one is a different color corresponds to the different well. So each well has each individual has different diversity, and then randomly combined individual the less diversified. I think that's what this experiment shows. So one of the discussion here is that it's quite difficult to say this, but there is a variation that exists from well to well. The variation within individual within the well is even greater. Variation among the individual is expected to increase. It's a difficult to say what this one is about, but when the very interesting point of this is the soup, which each individual has the same gene, right? Same DNA. So picking up one of them and start to let him divide. We did some up to the 4th generation. Then we make one single well that we put everything here. Right? Or maybe we can just pick up 8 different individuals and a single cell, and then compare this and this one. Then whether there's a difference or not. And one of the conclusions is that when you do this, this behavior is very much synchronized. Synchronized in the sense that they have always the same curve, the kinetic energy, so the similar curves. Because this something is inherited from the first pickup cell inherited something. So everybody has the same point property. But even if from the same gene pool picking up 8 one, then their behavior is very different sometimes. Although sometimes it's synchronized. But the question is, I think this one is of course it's characterized by the first cell, and this one is sometimes synchronized because there's an interaction, the strong interaction with each other. But this one is, I think this one has a strong interaction. And this one is a weak interaction. Because when the other one is the same to you or similar to you, I think the interaction becomes weak. This is sometimes anti-intuition. But if the other one is similar to you, they don't have to interact with each other. But this one, if the other one is very different from you, they tend to strongly interact with you. That makes synchronization sometimes. So it's quite difficult to prove whether this hypothesis is right or wrong. But one of the interesting points is that the characteristic of the single cell is even if without DNA transfer, I mean, without any DNA difference of DNA. So this one and this one and this one has the same DNA totally. However, something is different. Therefore, it is inherited from here to here to here. And this one has the same DNA, but it's a different phenotype, so that they have different. However, as time goes by, this sometimes it's synchronized because it's a strong interaction. But this one has a weak interaction because they are equal to each other. So they know the other one is your brother, so that they don't interact so much. Is my conclusion from here. And then I think so the vitality of the agent is probably measured by how, if this one goes this, is more vital, and this one goes down, is more inactive, it's not vital. But your vitality goes up if there is some good active agent exists in the well, so that they are synchronized. But for these guys, they are already determined by whether your ancestor is very active or not. So even if the gene is the same, that's the point. Even if you have the same gene, but once your phenotype is not strong enough, then it's inherited to the offspring, unfortunately. But even if you are not so active in your phenotype, but there's some nice agent exists, then you can strongly interact, then you can get energy from them. So maybe the message from this is that if you have to find your good friend, active friend, then you can be active, or you can be genki if your friend is genki, right? But then of course you cannot select your parents, right? It's a destiny, right? So that even if the DNA is the same, your phenotype is going to be different. But one of the remedy or something is that you see here that the first parent is like this, and then second generation, apparently they inherited behavior. And the third generation, some of them have a different distribution. Therefore, maybe there is some modification in this, right? Which I didn't understand still. So even if you inherit the same properties, but interaction with each other can change its activities. So you don't have to, regret that your parents are not so good, because your interaction with your brother or your sister can change your phenotype activity, so that you can still be very inactive shape, right? But sometimes, it's totally inherited, right? So everybody has the same activity. So in this case, even if you interact with your brother or sister, you cannot change your phenotypic activity, I think. So, but still, I don't understand. If you really want to understand this one, you have to understand the quality of what you mean by weak interaction and what you mean by the strong interactions. And theoretically speaking, I don't understand what this one is. Right? But it's not a simple synchronization. This one also has a synchronization, but apparently the synchronization is coming from, because they are coming from the same ancestor. But this one is maybe synchronized because of the interaction, I think. But we are not quite sure what's going on here. That's one of my questions. And and this kind of thing, I don't understand why this one happens. Because it's not always happens, but sometimes it happens. Right? This kind of synchronization only happens once, and it's not happens all the time. So this one, it's very strange that this one happens, because it's not so much close to each other, right? But it happened to show this kind of. It's not the issue coupling, not because you visually couple together, but some other reasons that they can show together. So we cannot explain that yet, but maybe it's by accident that they can show this, or maybe some other reason that I don't know. But anyway, that's kind of my talk, and it's my. Thank you. Yes.
I have a question from our really but when you turn on the video, it was not. Could you be the vibration that change mechanism? I mean, you have something that is not ice cream. But could it be that something is vibrating low? I mean, there's like a wave in this.
Even mechanical waves.
Yeah, mechanical waves that you maybe don't see the water, but there is something that.
Oh, that's interesting, but I haven't checked it, so I will do that. Yeah, so maybe this mechanical waves can connect one individual to another individual. That's what I'm saying, right? Because in the same oscillatory dynamics, that's why it's not coming. Maybe that's true. Yeah, maybe.
I don't know.
Yeah.
I guess it's the techniques don't try to.
Yeah. Thanks so much. Yes.
Maybe there are questions
Yeah.
from the web.
Yes.
You have a question from the web? Any questions from the people connected online?
Sorry, I wasn't so much clear on what I was saying, but.
Any questions from some people connected online?
John McCaskill has a question, I think.
John, yeah, please, John.
John?
John McCaskill.
Oh, okay, I see.
Yes, John.
He's on mute, I'm afraid.
Yes.
Now it works. Okay, thank you. Yeah, I wasn't allowed to unmute. Takeshi, thank you very much for the talk.
Hi.
I'm intrigued by this last part, especially. Lots of echoes going on here. Is that better? Is that any better now? Maybe the computer is close to the microphone. That's the problem there. Might be better now. Is that right? No.
Okay. Yeah.
Okay. Well, I'll try anyway. I'll speak slowly. The question is the relationship between what you're seeing and the evolutionary history of the tetrahymena. And the question, which is kind of intriguing, is whether or not this phenomena that you're observing is a result of a long-term but hard to measure kin selection happening within tetrahymena, so that there is a sort of evolutionary pressure for selection of recent kin going on, and so that what you're seeing could in principle be measured if you had a rapid mutating sort of neutral gene marker or some other mechanism for individually marking the changes, and to look at the correlations between selection and this rapidly changing marker. Because but I don't know whether the kin selection community have looked at sort of hidden kin selection things in such organisms. Can perhaps you know about this?
Yeah. As far as I know, I don't think there is a people studying a kin selection of tetrahymena. Also, my big question is how they sort of, for example, like Libra's group studied inheritance of, even if the same gene, there's something is inherited, but only when there's an isolated agent exists. But here, there's a bunch of neighbors. I mean, his brothers and sisters are interacting with each other.
So
Still, they can preserve their property. So it's a phenotype property is somehow inherited, even though there's an interaction with each other. That's something. To me, it's mysterious. And then, as you said, maybe this is can be explained through the kin selection of the heterohymenoid group, because they are in a group, right? So this group is the kind of unit that can select and then can, makes this inheritance stronger by when they are existing isolated.
But your experiment showed that it wasn't just group selection, because the closely related individuals who came from the immediate progeny did behave collectively in a way that your individuals who were drawn from a clonal population and were presumably more distant relatives clonally, although they had the same genome, but we're talking about the non-genetic inheritance here. Anyway, your experiment seems to show that it could be a form of more of kin selection than group selection, if you want to use the traditional.
I see. I'll check it out. Yes, thanks so much.
Thank you, John. Other questions? Well, I have a question related to John's question.
Yes.
So how long do you think this, because this memory of the fact that you come from the same ancestor presumably will fade away as as the time goes by. So is there a time scale that you have? So
interestingly, this when you are starting from the same single cell and then dividing into 2, 3, 4, 1, 8, I think even longer period of time that this inheritance seems to exist. Yeah, but for the behavior itself, it seems like it at least like more than 10 hours that exists. But which is it's a huge time compared to the time scale of the system, right? Yeah, that's right. So usually this behavior goes to the stationary state after 15 minutes, right? Yeah, but then this inherited behavior can sustain for a longer period of time. I think it's because of this interaction, this inheritance is enhanced. And then without the interaction with the brothers and sisters, maybe they lose their memory. So that's my guess, but I'm not sure. And then for independent case, they seem to synchronize, means that they are forgetting their individual properties. Right? Yes. After like 1 hour and a half, if you think all agents at the same time, then they seem to forget their phenotypic uniqueness after 90 minutes. Yes. So interaction helps agents to keep their memory, which is it's not a group, it's not individual DNA supported memory, but it's a somatic memory or something. It's inherited by the interaction. That's my guess from this one, but weak interaction is good for keeping somatic memory. Okay, so if there are no further questions, let's thank Takeshi for this fascinating talks. Let's thank him again. And thank you all for being with us, to people that were connected. And bye-bye. Until next time. Bye, John. Yeah, it's nice.
Bye.
Yes.
Thank you.
Thank you.
So in my language, this difference between weak interactions and strong interactions is the self-averaging breaking. Because in one case you have a time evolution, and you take some sort of average, with the same. The other one you make replicas, and then you take the average of the replicas. So it's effectively the self-averaging breaking.
Maybe. Yeah, that can be applicable. Yes. Yes.
Okay, grazie.